Okay, so we are going to continue our discussion of divide and conquer algorithms by applying divide and conquer algorithmic techniques to a problem that everyone is hopefully already familiar with, namely multiplication. Okay, so simple multiplication. You have two integers, b and c, with n digits each, and we need to compute the number b times c. Pretty simple. Okay, so what do we do? How do we compute this number? Well, we have an example from 4,000 years ago with the ancient Egyptians on how they computed two large numbers together. And in their case, the large numbers they want to compute together is 76 times 35. Okay, so unlike us, which who memorize our times tables and have several more advanced arithmetic methods to multiply these two numbers together. The ancient Egyptians didn't want to multiply 76 times 35 together right away. Instead, they wanted to reduce the multiplication into something simpler. Namely, they wanted to reduce multiplication of two largish numbers into the multiplication of two smaller numbers, or a multiplication of twos. Okay, so the first thing the ancient Egyptians did was try to make one of the operands or both of the operands even. Specifically, we want to get rid of this 35. 35 isn't a fun number to multiply with. So what do? Well, we realize that 76 times 35 is simply 76 times 34 plus 1. And to get rid of that plus 1, we just take out the 76 and put it in the addition pool. We're going to add that to the total result later. So now so now all we need to do is multiply 76 times 34. Okay, so multiplying 76 times 34 isn't too much easier, but the nice thing here is that we could take factors from 34 and give them to 76, making one of the numbers very large and one of the numbers very small. Hopefully, we'll make the second operand small enough to the point where the multiplication becomes trivial, right? So to show you what I'm saying is that we take a 2 from the 34, make it 17, and we give that 2 to the 76 and make it 152. Okay, so again, we're still multiplying the same, we're still getting this, need to get the same value, but the idea is multiplying 152 times 17 is easier than multiplying 76 times 34. And I think most of us would agree with that, right? So the next thing we do, again, 17 is an ugly number to multiply with. So all we need to do is take the 1 out of the 17. And in order to take the 1 out, we just take 152 and add it to our addition pool. And so once we have these numbers in our addition pool that we'll work with later, all we need to do is calculate 152 times 16. And in order to do that, we simply take 2 out of 16 and put it into 152. To make 304 times 8. Take the 2 out of the 8, put it into the 304 to make 608 times 4. And take the 2 out of the 4, put it into 608 to make 1216 times 2. And finally, 1216 times 2, we could take the 2 out of that, put it in 1216 to make 2432 times 1. And now we have, to get rid of that 1, we add 2432 to the addition pool. And so our total number is simply 76 plus 152 plus 2432 together, which gives you 2660. Right? So this is the way the Egyptians multiplied two large numbers together. Again, it's not too shabby. It's better than doing it straightforward, and they didn't have the partial multiplication techniques that we have today. So it is fairly clever, right? The process is fairly clever. It's an iterative process. It's making it more simple. It's making a complex problem and reducing it to multiple simpler ones, which is a beautiful thing, which is what algorithms is all about, which is what we discussed in our reduction lecture. But we, of course, have more complex numbers. Specifically, We have more complex methods. Specifically, we have grade school multiplication, which is simply the partial product method. And the partial product method is just the observation that you could multiply one digit at a time. You could take one digit from the operand and multiply it at a time, as long as you ensure that the order of magnitude is maintained. So you start with the digit in the smallest order of magnitude 8. You multiply 8 times 3141 to get 25,128, and that's it, right? Then you take the next digit, 1, and you notice that it is in the tens order of magnitude. So you shift the result of this multiplication, 1 times 3141, over by 1. Okay. Same thing when you look at the 7. You notice it's in the hundreds order of magnitude. So you multiply 3141 times 7 to get 21,987 and shift it over by 2. And then you do the same thing for the last digit too. And then if I add the partial products together to get 85, 37, 23, 8. Okay. So the nice thing is that this partial product method is not only faster, it's much more powerful. Could you imagine multiplying 3142 times 2718 using the Egyptian multiplication system? It would be nuts. You would be taking twos from the from operand 2 to and putting it into operand A for days, right? You can't do this with numbers that are 4, 5, 6 digits long. But the partial product method does let you work with those numbers fairly easily. It's not pleasant, but it's pretty easy. So the question is, how fast is grade school multiplication? In grade school multiplication is, well, we could analyze it. Let's see, every step, this takes O of n time because we're multiplying a single number times n digits. This also takes O of n time. This also takes O of n time. And then this also takes O of n time. And you do O of n calculation n times. So how fast is grade school multiplication of two n-digit numbers? It's n squared. Okay? Okay, but we want to do something better. Okay, so what do? Well, let's see if we could add some divide and conquer flavor into our multiplication algorithm. And specifically, let's look and say that we have two operands, B and C. And divide and conquer typically breaks the inputs up into two chunks, and hopefully equal size chunks. So for the sake of simplicity, for the moment, we're going to assume that the number of digits in n is a power of 2. And we're going to say that b, the number b, is simply the left side, the left half of b, shifted over a couple of digits, shifted over n over 2 digits, plus the right-hand side of b. Same thing with c. C is simply the left half of C that's been shifted over a couple digits, that's been shifted over to the correct order of magnitude, plus the right-hand side of C. Okay? And x, in this case, is, of course, 10 to the n over 2. So let's look at how this algorithm would work. We have two numbers, 1234 times 5678. Right? And we want to divide and conquer. So we break this 4-digit number up into two-digit numbers. So we have if 1234 is equal to 12 times x plus 34, where x is 100. Okay. Same thing for 5678. We have 5678 is the equivalent of 56 times x, 56 times 100 plus 78, right? So far so good. We didn't really do anything different, right? So the question is, we multiply these two things together, and as we know from our distributive rule that we have to multiply 12x times 56x and times 78. So we got 12 times 56x squared plus 12 times 78x. Okay, same thing with 34. 34 times 56x plus 34 times 78. Okay? And if we do all that, we get the correct result. Okay? Now, the question is, how fast is this? How fast is multiplying two numbers together by breaking them up into a left half and a right half? Okay? Well, here's the thing. We have 4 recursive multiplications. Okay? Now, each of these multiplications are smaller because the multiplications are for n over 2 digit numbers. And that's good that we do break them up into smaller multiplications. So on that front, the divide and conquer is helping us. On the other hand, if we want to write out the well, before we get there, we know that we have 4 additions and we know that we have a couple left shifts, okay? But specifically the 4 additions, how long does this take? Well, considering each addition could be the addition of 2 n-digit numbers, it could be at least 4 times n, or O to the n work, right? And the shift also gets captured in this O to the n work. Okay, so the recurrence for this, our divide and conquer approach, looks like so. And actually, if we do it out, the recurrence is equal to O, or even there's a lower bound, theta of n squared. Okay, so doing this divide and conquer approach doesn't really help us because we still have 4 recursive multiplication calls, which isn't ideal. Okay, that's the thing that's screwing us over. This right here, this still gets us to n squared, and that is not good. But a genius named Kartsubas came up, used this insight and other insights to come up with a very clever algorithm. Okay, so let's go back to let's take a detour. Let's take a brief detour and think about what happens when we multiply 2 complex numbers. Okay, when we multiply 2 complex numbers, we have a real part and an imaginary part, and a real part and imaginary part. And when we multiply the complex numbers, we get real part, imaginary part, real part, imaginary part. Okay, now, how many multiplications do we need to calculate this imaginary number? And the answer is, the clever thing is, we actually only need 3. Why do we only need 3? Why do we only need 3? This was Kartsubas' big insight, which was that, yes, ax plus b times cx plus d is this, right? We multiply these and we could have 4 multiplications here, okay? But we could rewrite this term. We could rewrite this term as a plus b times c plus d minus ac minus bd. Okay? Because we know a plus b times c plus d is equal to, again, just to drive the point home, AC plus AD plus BC plus BD. Okay? But if we want this number here, AD plus BC, all we need to do is take these numbers and take them to the other side of the equality and say A plus B times C plus D is plus or minus AC minus BD is equal to AD plus BC, which is exactly this. Okay, so we replace this term with this term. Now, why would we do that? Why would we do that when this looks so much more complex than this? This is so much more complex than this, but it's actually not. You know why? Because we've already calculated AC here. We've already calculated B times D here. So the only additional multiplication that we need to calculate is A plus B times B, C plus D. So we are reducing the number of multiplications that we need. But even though we're increasing the number of additions and subtractions, that reduction in multiplications is huge because it reduces the number of recursive calls. Recursive calls are way more expensive than a few extra additions and subtractions. Okay? So we could derive out this expression. Oh, we could go back to our divide and conquer multiplication and have a left part, right part, left part, right part. We have the normal form, divide and conquer form that we get just from distributing the terms. But instead of this term here, BL times CR plus BR times CL, we replace it with this. Okay, that's Kartsuba's advice. That's Kartsuba's insight. Sorry, to multiplication, that we could reduce the number of recursive multiplication calls by adding only a few more additions and subtractions. Okay, so timing analysis wise, the recurrence still has this O of n work. Okay, we do have more additions and more subtractions, but there's a constant amount more. Okay, and again, remember, n grows and constants stay the same. So as the number of digits in the numbers grow, whatever that constant amount of work is, it won't matter. It won't matter over time. And so calculating out this recurrence, we get that T n n is equal to O to the n log 2 of 3, which is also equal to O to the n to the roughly 1.585. Okay? So that's cool, right? We're able to multiply two numbers together in less than n squared time. So that's Kartsuba's algorithm. And the unfortunate, Kartsubas. I'm sorry, I keep saying Kartsubas. Kartsubas. Well, I'm going to leave that in there. Sorry, Kartsuba. That's Kartsuba's algorithm. So the unfortunate thing about Kartsuba's algorithm is that it's not the fastest multiplication algorithm anymore. It was when he first proposed it. But since then, there have been faster multiplication algorithms proposed, namely Schlage and Strassen is proposed in 1971. Soon after he proposed the faster multiplication algorithm, these two guys proposed an algorithm that multiplies two n-digit numbers in O of n log n times log n time using fast Fourier transforms. Martin Feuer recently, in 2007, well, actually not that recently, 20 years ago, but in 2007 proposed an algorithm that runs in O of n log n times 2 to the O log star n time. So this function itself grows very, very slowly. So very, very close to n log n. So many computer scientists believe that there does exist O of n log n time, but it hasn't been proven yet. And who knows, maybe you guys will be the first ones to do it now. Okay? So anyway, this right here is Kartsuba's algorithm for multiplying two n-digit numbers together. It is beautifully simple, incredibly clever, and that's why we're teaching it in this course. just the beauty and simplicity of recognizing A, that you could break inputs up into partitions and attack those partitions, and B, that you could that it is worth sacrificing a bit of work or adding a bit of work in order to reduce the number of recursive calls. Um, these two things matter, and they're good lessons for you to learn, even though you probably won't ever have to program this yourself. But it is useful to know just from the principles it teaches. Okay, thanks.